So just students, colleagues, and all the viewers who are watching this program live on Facebook page, Physics Adda, I'd like to welcome you all to my webinar. Good morning to all here in Bangladesh, and good afternoon to all those who are watching this program live from Japan. Hope you are well and safe from Corona pandemic. Today, I'd like to welcome you all to a joint session between the Pabna University of Science and Technology, Pabna, Bangladesh, and University of Tokyo, Japan, on a webinar in nuclear and particle physics and astroparticle physics. And we have with us here today Dr. Koichi Hamaguchi-san, Associate Professor, Department of Physics, University of Tokyo, Japan, joining us from Tokyo, Japan through StreamYard. And he have already connected with us, so I'd like to welcome him. So good afternoon, Koichi-san.
Hello, hi.
Hello, hi. So welcome to our webinar and welcome to Bangladesh through online.
Yeah, thank you.
So I think this program is going to be your first collaborating program with any Bangladeshi university, isn't it, sir?
I guess so, yeah.
Okay.
That's right.
So it is also a very special day for our department, and that because we are making history in our by arranging a StreamYard with a faculty member from Tokyo University, and it will be a memorable day for our department. And we know you are too busy with your research at the University of Tokyo, and I'd like to say thank you on the behalf of the Department of Physics, Pabna University of Science and Technology. And all we know that we are living in a Corona pandemic situation, and all the institutions have been shut down since March 2020 due to Corona pandemic. So it's very difficult for us to continue the academic program and research inside the university. So due to this problem, actually, we have arranged some online program, including online classes, online seminar and webinar. And in those online seminar and webinar, the physicists from different countries are taking part as a main speaker, and some will also take part in future. And you have already known that the student from different university also connected with this program. And in that continuity, today we have got one of the best nuclear physicists in the world, in Japan also, Dr. Koichi Hamaguchi-san, as a main speaker of our webinar. And I hope this webinar will help our students a lot, and it will create an opportunity for our students to interact with such a big nuclear physicist, and they can directly actually interact with him. So you have already know that we have divided our webinar in 3 parts. So first, I would like to introduce our speaker with our student and the viewers, and then the speaker will deliver his speech, and in the final session we have a discussion session where anybody can join with us, and that is question and answer session. So before going to our today's speaker, I'd like to introduce our speaker with you all. So I think you have already came to know that the title of our today's webinar is the first 1 second of the early universe and the physics beyond the standard model. So all we already know about our previous webinar, that the Big Bang and the nuclear synthesis, and we'll a little bit learn today more about this nuclear synthesis and the physics beyond the standard model with the help of our today's speakers, Dr. Koichi Hamaguchi-san. So before going that, I would like to say something about his academic and position. So Dr. Koichi Hamaguchi-san is currently working as an associate professor, Department of Physics, University of Tokyo. And if we go his educational background, he has completed his Bachelor of Science in Physics from University of Tokyo, and Master of Science in Physics from the Tokyo University, and also his PhD from Tokyo University. And then he has some postdoc from Tokyo University and Daisy group, Daisy theory group, and he joined as a staff member in Daisy theory group, and then he joined as an associate professor in 2006 at the Department of Physics, University of Tokyo. So we can see his specialty is particle physics theory, and research theme is particle physics, phenomenology, and cosmology. Keywords is physics beyond the standard model of particle physics, supersymmetric models, grand unified theory, dark matter, and its signature. Then baryonics inflation. So current research physics beyond the standard model, in particular Schucy model and their LHC phenomenology and application to cosmology. Then Big Bang nucleosynthesis constraints, dark matter and its signature. Keywords: physics beyond the standard model of particle physics, supersymmetric model, grand unified theory, dark matter and its signature, baryogenesis and inflation. So thanks all. So now we need to go our speaker. So I'd like to welcome again our today's speaker, Koichi Hamaguchi-san. Good afternoon here there in Japan.
Yeah.
So I'd like to welcome you again. You can start your session.
Okay. So can you hear me?
Yeah, I can.
Yeah.
Clear.
So, okay. So I don't know how do I know the reactions? Maybe you see some.
Yeah, I can help you in that regard.
Okay. So I heard that there will be a discussion or the question session after this seminar. But if you have question in the meantime, yeah, maybe you can also interrupt in between, because it's I don't know, it's 40 minutes, 1 hour.
Yeah.
So yeah, okay, let's get started then. So the title is the first 1 second of the early universe and physics beyond the standard model. So I like to start from the generic elementary particles. So I guess all you know that basically we are all composed of atoms, and atoms are composed of electrons and nucleons, and the nucleus is made of proton and neutron. And actually, proton neutrons are not the elementary particles in the current understanding, and they are also made of something, and they are called quarks. There are 3 quarks in the protons and neutrons, and there are actually 2 kinds of quarks, up quark and down quark. So this up quark has a charge 1/3, and down quark has charge -2/3. So by depending on the combination, it can become charge 1 proton or charge 0 neutron. So in some sense, you can say that we are all made of quark and electron. And you can also see that there are up quark and down quark has some kind of pair. They form a pair. And actually, electron has also a partner, like up and down quark. And it's called neutrino. So up and down quarks form a pair, and electron and neutrino form a pair, and it's called lepton. So technically speaking, this up-down quark interact or exchange each other by the weak boson, and likewise electron and neutrino can convert to each other by the weak interaction. So there are quarks and leptons. Somehow it's also known that there are 3 generations of quarks and leptons. So like up quark, there are 2 more quarks, and something like down quark, there are 2 more quarks. And in total, there are 6 kinds of quarks, and there are also 6 kinds of leptons. So, and they have all the same properties except for their masses. So they are very similar to each other, but somehow only the mass and interactions, a little bit of interaction is different. And we don't know why there are 3. Why not 2? Why not 4? There are just 3 generations, and that's one of the big mysteries of the standard model. But yeah, somehow we know that there are 3 generations of quarks and leptons. And in addition, there are gauge bosons. there are gluons and photons and weak bosons, ZW bosons. And if you know that there are three kinds of forces in elementary particle physics, these three kinds of interactions mediate the interactions. The gauge bosons mediate interactions. The gluon mediate the strong interaction, photon mediate the electromagnetic interaction, and WZ boson, the weak boson, mediates what is called weak interaction. And then finally, there is a Higgs boson that gives masses to all these particles, massive particles, and this is called the standard model of particle physics. So we have three generations of quarks and leptons, three kinds of gauge bosons that mediate three kinds of forces, and the Higgs boson. And so that's all particles in the standard model. And this Higgs boson was discovered in 2012. So that was the last particle, but it was eventually found like 8 years ago. So let me briefly comment on this Higgs field. So how it gives the masses to the other particles. So for instance, the electron also gets a mass from the Higgs field. So there are several ways to explain it, but let me explain in the following way. So electron has two components, the right-handed component and left-handed component. And actually, so the spin, the fermions have spins, and the right-hand component is in some spinning right-handed way, and left-handed component in left-handed. And they have different properties. The right-handed guy is not weakly interacting, and left-handed guy component has weakly interacting. So for instance, as I said, electron can convert to the neutrino, but only the left-handed component can be interacting with the neutrino or can be converted to the neutrino, but right-handed component, they cannot interact with the neutrino. So it has two components. Now, without the Higgs field, actually, the standard model tells us that these two components of electron, right-handed and left-handed, are different particles. So if there were no Higgs field, they are actually completely different particles. They have different properties. One is interacting with neutrino, and the other is not interacting with neutrino. And they have zero masses, actually, if there is no Higgs field. So therefore, they are moving with the speed of light, and therefore they can somehow preserve the spin. The right-handed guy is always right-handed, left-handed guy is always left-handed. That's possible because they are massless. Now with the Higgs field, what Higgs field does is it connects the right-handed and left-handed component with the Yukawa interaction. And because of this Higgs interaction, the right-handed and left-handed component can be converted to each other. And because of the Higgs condensation in vacuum, this is a bit difficult concept, but everywhere in our universe, in all space-time, the Higgs field has a non-zero value. And because of that Higgs field condensation, the right-handed guy and left-handed guy can be converted to each other everywhere in any space-time, and therefore they are mixed. The right-handed guy and left-handed guy are mixed, and in that way they get the mass. So maybe you have seen this kind of figure that if you're surrounded by some other guys, it's difficult to move. And in this way, because of the Higgs field, everywhere the left-handed and right-handed can be converted, and they become massive. Anyway, so somehow in this way, the Higgs field gives to all particles masses, and it was found in 8 years ago, and the last piece of the standard model was found. So in that sense, you may think this is the end of the story for the elementary particle physics. But actually, this is not the end. There are many puzzles in the standard model. So here I listed some hints of the what is called physics beyond the standard model. Sometimes it's called BSM, beyond the standard model. And there are hints from cosmology and hints from particle physics. And today, because of time, I cannot explain everything, but I explain some of them depending on the time, and some motivations why we think something beyond standard model is necessary, and some candidates of possible solutions for these puzzles. Okay. So far, it's okay. No,
Okay,
no problem.
okay.
Yeah.
No.
Then I continue. Okay. So yeah, I want to start from here. So there may be a bit theoretical, but starting from quark-lepton properties. So as I said, the electron gets a mass from the Higgs field, and left and right component mixed by the Higgs field, and it applies to all other quarks and leptons. All quarks and leptons similarly have a mass from the Higgs field, and there are left-hand component and right-hand component for all quarks and leptons. So if you write this first generation up quark, down quark electron in terms of this left and right components, then it becomes like this. So this is left-handed quark, right-handed up quark, right-handed down quark, left-handed lepton, right-handed lepton. So as you can see there, it's a bit complicated and not completely left-right symmetric, but this is the what we know from the standard model. And there are some complicated numbers around here, but it's not necessary to understand the details. But I want to say something about it. So this left-handed quark, they form this up-down pairing, and it's represented by this 2 in the second component of parenthesis. And also, as I said, electron neutrino has a pairing, and it's also 2. So it's doublet in terms of the SU2 group. Anyway, these left-handed components, they interact with a weak interaction. So they can be converted to each other by exchanging the W boson, for instance. On the other hand, these right-handed guys, quarks and leptons, they don't feel weak interaction. So they are different. They have different properties. Now, these quarks, they feel strong interaction, and leptons, they don't feel strong interaction. So it's represented by these 3 in the first component of parentheses. And finally, you can see this very complicated fractional numbers, 1/6, 2/3, 1/3, and so on. They correspond to the hypercharge. And it's kind of, it's some modified version of the electromagnetic interaction. But anyway, that's the standard model description. So as you can see, it's very complicated. There are many numbers, and quarks and leptons have many different properties, left and right. So it doesn't look like ultimate theory. It doesn't look like a fundamental theory. It's very kind of ugly. So the question is, any simple unified framework, unified theory to explain these very complicated numbers? And maybe there is. Actually, already the standard model is a kind of a unified theory. The electronic interaction, magnetic interactions is unified in electromagnetic interaction in terms of the Maxwell equation. And electromagnetic and weak interaction is unified in electro-weak interaction in the standard model. And there's one more idea to unify all three interactions, electromagnetic, weak, and strong interaction, into a single framework, what is called grand unified theory. And in terms of this grand unified theory, these complicated quarks and lepton quantum numbers are now unified into very simple framework, theoretical framework. For instance, if you say it is SU5 interaction, then just by saying it's a 10 and 5 of SU5, all these complicated quark-lepton quantum numbers are beautifully explained. For instance, just one example, this fractional charge 1/3 and minus one half, standard model cannot explain why it has such a strange number. But in terms of the grand unified theory, it requires that some of these charges should be zero in single representation, and therefore you can explain why it has this ratio 2 versus 3. So in this way, the SU5 grand unified theory can explain this complicated number. So that's one framework beyond the standard model. Now let's go to the neutrino mass. Maybe it's a different story, but you see it's somehow connected, related. So again, this complicated numbers, but you see that neutrino, this one, has only left-handed component. There's no right-handed neutrino in this standard model. So as I said, if you remember the electron case, the electron has a left-hand and right-hand component, and they get a mass. But neutrino has only left-handed component. So in the standard model, it's massless. But of course, we know that neutrinos have masses from neutrino oscillation, like discovered in Super Kamiokande. So standard model cannot explain the neutrino mass. So we have to go beyond the standard model in that sense. And very simple solution is to add just right-handed component. So from other quarks and leptons, we already know that to get a mass, you need a left and right-handed component. And neutrino has only left-handed component. So why not just adding right-handed neutrino? So this is a very simple solution, and you may think it's trivial. But actually, this right-hand neutrino is a very important particle. Maybe it's very important. Actually, it plays a triple role. It has three good things for the physics beyond the standard model. So number one, it unifies quarks and leptons further. So as I said, SU5 grand unified theory unifies these quarks and leptons in a very simple way. But if you add this right-hand neutrino, it becomes 10 plus 5 plus 1, so it's 16. And actually, in mathematical language, in group theory, this 16 is a single representation of the SO10. So in other words, if you just say all quarks and leptons are 16 representation of the SO10, then it can explain all these complicated quantum numbers without any assumption. All those strong interaction, weak interaction, fractional charge is just 16 of SO10. And just for illustration, if you put 5 arrows up and down with an even number of upward arrow, then there are 16 possibilities, 2 to 4. And then you can regard this, each of them are quarks and leptons. So for instance, around here, you can see that the up-down becomes down-up, so it's a weak doublet. Or in this right arrows, 3 arrows correspond to the SU3, strong interaction. So just putting up and down 16 ways, you can beautifully explain the properties of the quarks and leptons. So this is, I think, very nice. And as you see, the right-hand neutrino plays a very important role to unify everything in a very simple representation. That's one thing. And secondly, not only it explains the neutrino mass, but it explains why it's so small. So this I showed all quarks lepton masses. So electron has mass just below MeV, and the heaviest guy, top quark, has around 100 GeV. So it's about 5 orders magnitude between the lightest and heaviest quarks and leptons. But neutrino, they have masses below 0.1 electron volt. All three neutrinos are very, very light. So you see, the quarks, leptons have the only neutrino has very, very small mass compared to the other guys. And of course, standard model cannot explain the reason why only neutrino has so different. And so that is one puzzle. But right-hand neutrino can also explain it, because this right-hand neutrino, you can see this number 110 means that it has no charge, it has no weak interaction, it has no strong interaction. It's completely neutral. It has no quantum number in terms of the gauge interaction. So in that sense, it can be its own antiparticle. So it's possible only for this guy, but somehow because of this quantum number, it can be its own particle, its own antiparticle. Then you don't need a Higgs to have a mass. So the right-hand neutrino can have its own mass without Higgs field. Then this right-hand neutrino can also have a mass with the left-hand guy with the Higgs field, and somehow the light neutrino in this outside, this is a kind of Feynman diagram. They can have a mass in this kind of diagram, and if you calculate the mass, you see that what we observe as a neutrino mass is inversely proportional to the mass of this heavy right-hand neutrino. And because of its property, this guy can have a very heavy mass. And if this right-hand guy becomes heavy, then the left-hand guy becomes light. So it's called seesaw mechanism. One is heavy, one is light. Anyway, so in this way, this right-hand neutrino can also explain the size of the neutrino mass. And finally, as a third point, it can also explain something about the universe. So I will explain it later, but it also explains matter-antimatter asymmetry in our universe. So in that sense, this right-hand neutrino, I think, is a very attractive candidate because it has triple role. Okay, so back to this frame, I explained this grand unified theory and neutrino mass. Maybe it can be explained in terms of the right-hand neutrino, and it also nicely fits into the grand unified theory in terms of this SO10-16 framework. Okay, now, so I also changed a little bit of topic. Okay. So now I go to the cosmology. So in cosmology also there are several puzzles that point to the physics beyond the standard model. So I think I can explain only some of them, but let's start from the universe, our universe itself. So our universe is expanding. So if you put some point on the balloon and then expand the balloon, then you see these points separate each other. So we see this kind of thing in our universe. The farther galaxy goes faster to away from us, it's called Hubble expansion. So we know that our universe is expanding. That means that going back time, the universe shrinks. So in the early universe, our universe was in some sense smaller or denser, and therefore, if you go back and farther, the early universe was extremely hot and dense. Yeah, it's natural. Right? Everything it's going to close to each other. You may think that, but is it true? Any evidence for such a hot and dense universe? Because we haven't directly seen the early universe, of course. But actually, there's a evidence. Maybe you have you know that the photons emitted when the universe was around this time, 380,000 years old. So today's universe is this. What is this? 14 giga year. But much earlier time, around that time, the photon was emitted, and then we have seen we see that photon in today in present universe after this 14 giga year as a cosmic microwave background radiation. So this comes from everywhere in our universe, and this dots or these small squares, they correspond to the observation. So by the way, this is a frequency, x-axis a frequency, and y-axis the brightness of the photon. And this line corresponds to the prediction of the hot Big Bang universe. So you see the prediction of the hot Big Bang universe agree extremely well with the observation. So observation and the prediction match very well. So we have a clear evidence that universe was indeed very hot in the early time. Okay, now, okay, that was from 380,000 years old, kind of young universe, but then can we go back further, more even earlier time? And actually we can go much earlier time. The light elements were generated when the universe was around 1 second or about 1,000 seconds, and in very early universe. And around that time, this like helium-4 or helium or lithium were formed, and you can calculate how much of them were formed by using the thermodynamics, Einstein equation, nuclear physics, and so on. And again, the prediction agree very well with the observation. We now see such an helium and lithium in our present universe, and we can compare it with the calculation based on this hot Big Bang universe, and it agrees very well. So again, we have a clear evidence that the universe was indeed very hot. At the time, it was just 1 second from the beginning. So I think it's amazing, but we have clear evidence for such stuff. Okay, then what about even earlier, the first 1 second? So that's kind of my main topic, one of main topics of today's today. And there's no direct evidence what happened in the first 1 second. So in some sense, we have a evidence after 1 second, but the very first 1 second, we have no clear evidence like Big Bang nuclear synthesis or CMB. On the other hand, there are puzzles that cannot be solved unless we understand this first 1 second. So this first 1 second is very important to understand the mysteries of the universe. So maybe you have seen this kind of figure before. This is the energy fraction, energy budget of our universe. And there are only 5% for no matter. No matter means that like protons, neutrons, and electrons. But the rest 95% is unknown. And 20% is dark matter, and 68% is dark energy. So we don't know why there's only matter and no antimatter. We don't know what is dark matter. We don't know what is dark energy. Also, there's problems of initial condition of the universe, how the universe was started at the beginning. So these are the puzzles in our universe, and we have to understand the first 1 second to understand. We have to the first 1 second plays the key role to understand these puzzles. So let's discuss this 5%. Why no antimatter? So this is the table of the quarks and leptons in the standard model, and each of them has its own antiparticle. So up quark has partner anti-up quark, or electron has its partner positron, and so on. So all they have antiparticle. So it's also theoretically established, and also experimentally all these antiparticles are already found in accelerator physics and so on. For instance, electron has a charge -1 and positron has a charge +1. They antiparticle each other, and apart from the charge, it has exactly the same property. The mass is the same, and so on. Spin is the same. Okay. And in the early universe, like let's say 0.000001 second, at that time, we can again extrapolate our understanding back in the early universe by using thermodynamics and so on. Then you see that the number of particles and number of antiparticles were almost the same at the time. So at the beginning, there are almost the same amount of matter and antimatter that we can calculate by using the Einstein equation in standard model. But somehow, there was a very small excess of matter over antimatter. So depending on how you count, there are 300 million antimatter versus 300 million plus one matter or something. Very, very small difference. But there is a small excess of matter over antimatter. And then when the universe got cooler and cooler by expansion, most of them go pair annihilation. So for instance, the electron and positron can pair annihilate into photon-photon, or like this. So all particles and antiparticles, most of them just annihilate each other and just disappear. And then this very small excess, 1 over 300 million, this small fraction remains. And we are made of from this leftover. So there's essentially no antimatter, and the only matter is present in our universe. So all of us, galaxy, the Earth, or ourselves, are made from this very small leftover of the matter. Compared to this starting point, it's very, very small fraction, but we are all made from this. So the problem, the puzzle, is that then how was this initial excess of matter created at the beginning? So if there were no such an excess, we cannot survive. So there's no galaxy, no Earth. So we cannot discuss physics, right? So this small excess was very, very important, but how or why such a excess was there from the beginning? Maybe you can think it's a very, very small fraction, 300,000, 300 million. It's just there from the beginning as an initial condition. But actually, it doesn't work. So today, I did not have time to discuss the inflation, but we also believe that there was an inflation at the very beginning, and inflation dilutes everything. So at the very beginning, the universe was not very hot, but it's just the vacuum energy, nothing. And you have to start from that a very empty vacuum energy universe. And therefore, you cannot prepare this matter-antimatter as an initial condition. You have to somehow create both matter and antimatter from this such a vacuum energy. This is related to the initial condition of the universe. But anyway, according to this inflation model, initial condition doesn't work. So we have to somehow create such an excess of matter over antimatter. And in general, such a mechanism is called baryogenesis. And nobody knows what is the real answer, but we have to consider some mechanism to create asymmetry. And it is known that the standard model cannot explain the baryogenesis. So technically speaking, it's known that there are three necessary conditions for such a baryogenesis. And Sakharov pointed out many years ago, and two of them are satisfied in the standard model, but the last one, out of equilibrium, is not satisfied. Also, the second condition, CP violation, is it's too small to explain the amount of baryon asymmetry. So something beyond the standard model is necessary. And there are many candidates for this baryogenesis. And here again, this right-hand neutrino may be the solution. So as I said, right-hand neutrino is already attractive for the Grand unified theory and for the neutrino mass, but it can also explain the matter-antimatter symmetry of the universe. So because of its special property, as I said, this guy can be its own antiparticle. So it can decay into particle and antiparticle. For instance, it can decay into electron. It can also decay into positron because it is its own antiparticle. So it's called Majorana neutrino. So Majorana particle can decay into particle and antiparticle. And if CP violation is there, then the decay rate, probability of going to matter and probability going to antimatter can be different. For instance, you can think of, say, 51% going to matter, 49% into antimatter. So then there is a small excess of matter-antimatter asymmetry. So in this way, by the right-hand neutrino, you can explain matter-antimatter asymmetry in the universe. Okay, so yeah, initial condition of the universe requires inflation. Sorry, I didn't have time. But matter-antimatter asymmetry of the universe, together with the inflation, we need some kind of mechanism, baryogenesis. And actually, the right-hand neutrino may play a role here. Maybe it can also explain the matter-antimatter asymmetry of the universe. Okay, so finally, I briefly mentioned the dark matter. So I talked about this non-matter 5%. Now I want to talk about dark matter here. So what is dark matter? So yeah, dark matter, we know that there is a dark matter from many evidences, like rotation curve. For instance, this maybe you have heard it. If you look at the stars moving in galaxy, you see that without dark matter, you cannot explain the motion of these stars, and you can infer, you can guess the some gravitational force that somehow pull the stars, and it's called dark matter. And there are many other evidences like cosmic micro background, large scale structure, and this planet cluster. So we know that there is a dark matter, but we don't know what it is. We just know there is something, but we don't know what it is.
Okay.
Is okay?
Yeah.
Yeah. So I think I'll finish soon. So yeah, in the standard model, none of them can play the role of dark matter. So if you study them, it cannot be the dark matter. So we need again something beyond the standard model. So we need a new particle or something new. And again, there are many candidates, and one attractive candidate is what is called WIMP, weakly interacting massive particle. WIMP is attractive because it has what is called thermorelic scenario. So thermorelic scenario is like this. So this x-axis is the time, 1 over temperature, but it's essentially the cosmic time, and y-axis is dark matter number. Now, in the very early time, the dark matter was interacting with standard model particles like electron and photons. So they are in thermal equilibrium. So they are many dark matter at the beginning, but gradually they cooled and they pair annihilate. And at the end, they can no longer find each other to pair annihilate, and they just remain today. So in some sense, it was very hot at the beginning. It cooled and just decoupled from the other particles and now present in the present universe. And this kind of scenario we have already seen in the standard cosmology. One is the cosmic microwave background. As I said, photons, we see this photon spectrum in the present universe, and it was actually hot at the beginning. It interacts with the electron and proton, but once the atoms are formed, the universe becomes neutral and photon can freely propagate, and now we see CMB. That's one example. So we know already a very successful example of such a hot, cooled, and decoupled scenario. Another example is the Big Bang nucleosynthesis. So this also, as I said, at the very early universe, protons and neutrons are all in thermal equilibrium, and around the temperature of 1 MeV, or it corresponds to 1 second. Maybe you can see this is around 1 second. Then this helium, lithium, these light elements are formed, and we see it now. So we already know two very successful examples of such a thermal-redox scenario. So why not also dark matter? Maybe dark matter also follows a similar story, that it was hot and cooled and then decoupled. And if you calculate this number, then this weakly interacting particle having a mass around Higgs mass, it can nicely explain the amount of dark matter, abundance of dark matter. So that's why this WIMP is very attractive scenario for dark matter. Okay, so now I finish. Let me briefly summarize what I said. So the very complicated quark-lepton numbers may point to the grand unify theory, and neutrino mass can be explained by the right-hand neutrino. It somehow fits to the grand unify theory as well. And inflation is required. Sorry, I didn't explain it. And matter-antimatter symmetry requires some mechanism, and it can be all again from the right-handed neutrino. And dark matter, there are many candidates, but one attractive candidate is what is called WIMP, the thermal-redox scenario. Now, actually, there are some more stories. So if you're interested, maybe we can discuss it later. So, for instance, this inflation grand unify theory, right? And they point to very high energy scale compared to the Higgs mass. So it causes what is called Higgs naturalness or Higgs fine-tuning problem, and it may be solved by supersymmetry. And supersymmetry actually gives a very attractive candidate for WIMP. So it somehow gives a candidate for dark matter. And moreover, the supersymmetry is also very nicely fit to the idea of the grand unify theory in terms of the coupling unification. And finally, yeah, dark energy is a mystery, but I don't know. There are some solutions, but it's, I think, very difficult, maybe most difficult problem among this. So before finishing my talk, I have to say that one thing is that there are many experiments. I'm a theorist. I don't working on the theory, but experiment. But there are experimental searches like proton decay in Kamiokande or LHC at CERN, or many dark matter searches, neutrino restable beta decay, neutrino oscillation, and so on. So many experimental efforts done to search for this new physics. That's one thing. And also I want to emphasize that maybe these things, all these new physics candidates may be completely wrong. because it's all theory works. So unless we confirm by experiments or by other evidences, we cannot say. So maybe it's different story. So if you ask some other theorists, maybe he or she doesn't like supersymmetry, or maybe some granified theory is also one of the candidates. Ferrogenesis can be something different. So please note that all these things are one of the scenarios.
Yeah.
So hopefully maybe some of you in students may find in the near future something new scenarios. Okay, thank you very much. That's the end of my thought.
Yeah. Thank you, Kushida-san, for wonderful presentation. And I think all the students have benefited by your presentation. So if you allow me, then I can allow student ask question.
Yeah, sure. Yeah.
So we have already got some question from our Facebook comment. So first question, how do we sure about the existence of dark matter and by which theory?
By
How do you sure about the existence of dark matter and by which theory?
dark matter.
Existence of the dark matter.
Yeah. So one very popular thing is that this rotation curve. So if you think about two-body problem, the two massive particles interacting with each other by the gravitational force, then you can think of one particle going around this one particle, right? And you can, in that sense, guess just by looking at this rotating guy, how much the mass of this central guy, right? So without looking at this central guy, you can guess by looking at this velocity of this and radius, you can guess the mass of this central part. And you can see that thing in the galaxy. So you can see many stars moving in the galaxy, and you can guess how much mass is in the center. Then you see that the mass taken in that way is much larger than the mass of the visible particle, like stars and other things. So in that way, we see that something very dark, invisible, but massive should be there. That's from the rotation curve.
Okay.
Yeah.
So thank you. So we know that the universe is made from a Big Bang, and after that, in which stage dark matter and dark energy were made. So we know that in the beginning, all the we have already explained that matter and antimatter have created, and then in which stage that in which stage this dark matter and dark energy have were created.
Yeah, that's a very interesting question, and yeah, we don't know. We don't know. But for instance, in this WIMP scenario, one of the most attractive candidates, then this mass of dark matter is around the 100 GeV, meaning that it's 100 times the proton mass. It's as heavy as 100 times the proton mass. And then this thing, dark matter decoupling, happens like 0.1 times its mass.
Okay.
So when the temperature becomes as low as, let's say, I think it's around here.
Okay.
Yeah, actually, it's written here. Possible dark matter radius. Yeah.
Okay. So within 1 second.
That's right. Yeah, in the very early universe. Yes.
So in that picture, you have showed that there is interaction between two dark matter, and the electron and positron and two gamma come out. So is it the theoretical prediction or something like that? So in that slide, you showed that there is interaction between two dark matter.
Yeah. This
slide,
one. Yeah.
So is this just prediction, maybe a theoretical prediction, or is there any experimental evidence or?
Yeah, that's also a very good question. So to actually just the theory, no direct evidence. But to make this scenario successful, the dark matter should be annihilated into one of the standard model particle. So it can be electron, it can be quark, it can be photon, and actually typically quarks. I just wrote electron because of the simplicity, but it's actually quarks. And maybe if you can wait a little bit, I can show one figure that can I share another?
Yeah, of course, You can.
How can I
remove this one and then
share and okay, can I see?
Yeah, you can see now.
Yeah. So to make this WIMP scenario successful, as I said, it's typically dark matter pair annihilate into the standard model. So this is going to from top to bottom. So we usually assume this kind of interaction: dark matter, standard model. So standard model can be electron, positron, quark, lepton, everything. And if you assume this kind of interaction, interestingly, you can search for dark matter in various ways. So for instance, if you go back in time, then the standard model, by colliding standard model particle, you may be able to create dark matter at the laboratory. That is now searched in LHC, for instance. And if you go from left to right, then dark matter may scatter against the standard model particle. For instance, dark matter can scatter the nucleon, and that is done in various dark matter search experiments, like xenon experiment. Typically, it's deep in underground. And finally, dark matter may pair annihilate in the present universe. So although they are decoupled, some of them may be still pair annihilating. Then they can create cosmic ray. So by looking at the cosmic ray on sky, maybe you can see a signal of dark matter. So there are various ways of searching for dark matter. Yeah.
Okay, thank you. So to understand dark matter and dark energy, we need to go beyond the standard model, is it?
Yeah.
Okay. So we have another question in the inbox. So they want to know about, you have already talked about SU5, and they are interested to know about what is SU3 and SU5. SU5, you have told in your slide, SU5 interaction.
Yeah.
So they asked us that what is SU5 means or SU3 means.
Meaning.
Yeah, meaning or
of 3 and 5, for instance.
Yeah.
That's technically it's called the non-abelian gauge theory. Yeah. So for instance, within the standard model, we know that there are. So actually, going back to this figure. So as I said, there are quarks inside the proton and neutron, but there are 3 colors of quarks: red and green and blue, and they form what is called the multiplet, and they can convert to each other by the strong interaction. So the red quark can go into green quark can go to blue quark by exchanging the gluon. Now SU5 does similar thing by unifying quarks and leptons. So if you look at this figure, you see that originally the quarks and leptons are different particles, but in terms of the granify theory, is 5. All 5 particles here, for instance, lepton quarks are same particle. So now by exchanging new gauge in boson, the quark can go to lepton and lepton can go to quarks.
Okay.
Yeah.
So thank you. So there is another question in the Facebook. Could you shed some light on what supersymmetric theory is? Actually, he wants to know about the supersymmetric theory. So could you shed some light on what supersymmetric theory is?
What the supersymmetry
theory? Tuning. theory, supersymmetric theory.
Theory
Yeah.
by what?
So
What is
theory,
supersymmetry?
yeah. What is supersymmetric theory or something like?
Supersymmetry is a symmetry between fermion and boson.
Okay.
Let me try to find some slide. No, sorry, this is in Japanese.
Okay, no problem.
Yeah. I don't know if it helps. Let's see. Okay. Maybe I can share this screen. Can I?
Yeah, I think you can.
Can you see?
Yeah.
Yeah. So supersymmetry is a symmetry between fermion and boson. And so if you know the spin of, if you know the quantum mechanics, I think you learn the spin. And quarks and leptons are the fermions, so they have spin 1/2, like electron has spin 1/2. And Higgs boson, it's a boson, so it's spin 0. Now supersymmetry is a symmetry between fermion and boson. So for instance, quark has a partner called squark with a different spin, and Higgs has a partner, it's called Higgsino, with a different spin. And in this way, you somehow pair fermi and boson each other. And so roughly speaking, you have twice as many particles as the standard model. So you double the number of particles. So it's a bit very large theory.
Okay.
Yeah, and none of these new particles are found. So again, it may be completely wrong, but this supersymmetry does do several attractive things in the framework of new physics. So many people think, well, at least thought, it's a very attractive framework.
Okay. So thank you, sir. So there is another question. So how does neutrino oscillation predict the non-zero mass of neutrino? How
Okay.
does?
I don't have a slide for that.
And
So can I assume quantum mechanics?
yeah, of course you can.
Yeah. Then okay, it's basically interference of states. How can I explain it? I think you can find many web pages.
Okay, I think it's okay. I think,
Yeah.
There is another question. Thank you. So he wants to know. I don't know much about the relation between the cosmology and particle physics, but okay. So he wants to know, is there a relation between particle physics and cosmology?
Relation.
Yeah.
Yeah,
That's right.
that somehow, I explained. So you want, if you want to know the our universe, you have to know the particle physics, because it was very dense and hot. Yeah, so maybe I can share screen again. This one. So yeah, the yep. Yeah, so basically it's already particle physics here. So for instance, what happened in such a very hot universe, you have to know the interactions of particles with each other, and that's described by particle physics or nuclear physics. And we have evidence that this cosmology and particle physics or nuclear physics, this relation is very important, and it has already evidence. It's very successful. Yeah.
Okay, so thank you. So there is another question. So what is the quark-gluon plasma? One student actually want to know about. So
Yeah, quark gluon plasma is in the
inside that,
early universe. In the early universe, it's around here. I think it's
yeah,
just
that,
before 1 second.
yeah.
The protons and neutrons are not there anymore. They are kind of so it's so hot and dense, and the protons and neutrons are already broken, and the bare quarks and quarks and gluons are propagating each other because it's too hot to form a proton and neutron. And experimentally, you can also uh, try to make such a quark gluon plasma by smashing heavy nuclei, and that's been done, for instance, in RIC experiment.
Okay.
Yeah.
So thank you. So you have already explained about the baryogenesis and leptinogenesis. So could you
Mhm.
explain it again, because some student actually want to know those things again.
No,
Baryo,
could you say it again?
yeah, baryogenesis and yeah,
Yes.
leptogenesis.
Once again, or what is it?
Baryogenesis and leptogenesis.
The mechanism.
Yeah, yeah, mechanism.
Uh, you mean what is the leptogenesis, or
Yeah, yeah, yeah. What is leptogenesis and what is baryogenesis?
so?
And why these are important in this particle physics theory?
Yeah, we want to explain this asymmetry
Mhm.
baryon, the why this matter and more
And
matter over
yeah.
antimatter, and this standard model of particle physics cannot explain it. So
Mhm.
we have to have something beyond
Beyond,
the
okay.
standard model, and that is called baryogenesis. So
Yes.
it's a generic name, and leptogenesis is one of baryogenesis mechanism that comes from the decay of the right-hand neutrino. So it can decay into matter and antimatter with a different ratio. And if this happens in the very early universe, it can explain the amount of asymmetry. Is it answering the question?
Yeah.
I'm not sure.
No, no. It's okay. So thank you. I think all the questions have finished. So no more
Mhm.
questions. So I think we should finish the question session.
Mhm.
So thank you again, and I'd like to say thank on the behalf of the Department of Physics, Parma University of Science and Technology. So we know that you are too busy with your work, and
No.
after having so much work, you gave us time. So thanks for this. At the last, we have one question. So if you allow me, then I can read that question in the Facebook.
Mhm.
Okay. So if plasma is something where everything is in ionized state, so far there can we infer that charge of electron is not fundamental unit of charge, because quarks also need to go to their free state. So this is a big question.
Mm.
Can I read it again? So
Mhm.
if plasma is something where everything is in ionized state, so
Mhm.
far, so from there, can we infer that charge of electron is not the fundamental unit of charge, because quarks also need to go to their free state.
Mm. Sorry, I
Okay,
don't catch the.
okay,
uh,
we can discuss it later, because the question will remain in that page. So I think we can
is
discuss.
it already in the Facebook?
Yeah, yeah, in the Facebook you can see it. And
Okay,
another
then
question,
I can
why the
join the
shape of
discussion.
yeah, yeah, and why the shape of the galaxy are different? Another question.
Shape of the galaxies.
Yeah, shape.
That sorry, that's not
Yeah,
my
it's part of
expertise.
maybe cosmology. Okay,
Yeah, I don't know.
so
Sorry. Yeah.
thanks again. So and uh, for everything, and because we know that you are too busy, and you gave us and you accepted our proposal, and I think this program will help a lot of our students, and they
Thank
become
you.
so happy. and they can understand a lot of unknown things, mainly dark matter and the physics beyond the standard model. We know the physics within the standard model, and now they may understand the physics beyond the beyond the standard model, and about the dark matter, because all we know that about 95% are contain dark matter and dark energy. So we have to know about that 95%, and the our aim is to actually encourage our new generation, and actually the scientists like you actually accepted our proposal for encouraging our new generation, and that is very great things, and we are so grateful to you. And thanks again on the behalf of the Department of Physics from the University of Science and Technology. Hopefully, we will see you again, because you have some topics still remain, inflation and other. And there is a request from student also that you should, they are requesting, please bring him again. So I am requesting again that if you have some time, then please give us time in future. So thanks again. So see you and bye.
See you. Bye. Thank you.
Thank you.